This is a lecture on 7-3, confidence intervals and sample size for proportions. What we need to do is we are continuing with confidence intervals, but in this case we're looking at proportions. In order to study proportions, I first have to start with vocabulary and notation. We're going to use the letter P, which you've seen before as the probability of success. It is the same probability of success, except now we're going to call it population proportion. The little triangle on the top is called a hat. This is P hat. And it stands for sample proportion. In the case of confidence intervals, this is going to be our point estimate. In order to hypothesize or predict the population proportion, we need to start with something concrete, like a sample proportion. So you go out, ask enough people a yes or no question, because one of the assumptions is it is a binomial experiment, and I will write this down in a second. You will ask a question, and then you'll gather statistics on the fact that so many people answered yes to your question. You will use that, the sample proportion, as the point estimate of your confidence interval, where you can add or subtract the margin of error, and you will get your information, you will get your result. So this is where I write down all of that down. I have my P, I have the P hat. I also have a Q hat. A Q hat is 1 minus P hat. This is in a sense the probability of failure. So if I know it's gonna rain 60%, it's gonna rain, that means that there's 40% that it's not going to rain. If 60% of people said yes to my question, that means that 40% said no. The assumptions, there's two basic ones. It's a random sample. That one will always be assumed for all of the problems in this book. And two, this is a binomial experiment. Now, because it's a binomial experiment, everything goes along with the binomial experiment also follows. One of the biggest things is a binomial distribution can be well approximated with normal distribution. So using a z-score is the reason why it's in this book, because chapter 7 is all about normal distribution. 7.1 uses a z distribution, standard normal distribution, to approximate means. 7.2 uses a t distribution, which is still normal distribution, to approximate the mean when the standard deviation is unknown. And this one is also using the standard normal distribution to approximate under two conditions, which must be checked every time you're doing this problem. NPQ has to be greater than or equal to 5, and NP hat has to be greater than or equal to 5, and NQ hat has to be greater than or equal to 5. We've already seen this as part of 6-4, where we talked about approximating a binomial distribution with normal distribution. Let me just move my example a little further down. And formula. The P can be approximated by taking a P hat and adding the Z alpha over 2, so the Z that corresponds to the middle 90%, 95%. In the parentheses, you're going to have a P hat, Q hat divided by N. On the other side, you're going to have exactly the same thing, but with the minus sign. Vocabulary. This is now called margin of error. And this is called point estimate. What we're going to do is we're going to start with example 7-9. And the example says, a survey conducted by Salime and Gallup of 1,404 respondents found that 323 students paid for their education by student loans. Find the 90% confidence interval of the true proportion of students who paid for their education by student loans. So what we are given is some very important information. They gave me the number of people that they surveyed. What they also gave me is the number of people who said yes to my question. So this, I'll underline this with blue. Students paid for their education by student loan. That's my quote-unquote success. The next number is 323. That's the X. Because this is how many people said yes to my question. We're interested in 90% confidence. And some of the intermediate questions that might be asked is find the p hat, find the q hat. Sometimes they might ask it as, instead of find the p hat, it would say find the point estimate of the confidence interval. So the p hat is constructed by taking the number of people that answered yes to your question and divided by the number of people that are asked a question. So I'm taking out my calculator. 3 to 3 divided by 404. I have approximately 23%. I do have a bunch of zeros and I have a 56, so this is fine. What this means, I'll put an equal sign because this is enough. In order for me to find q hat, all I have to do is just 1 minus 0.023. And I will get 77% who answered no. In order to find the z alpha over 2, you can look up under inverse norm of the middle 90%. Or what we can do is we can actually go into stat, go over to tests. What you need is you need a button that's called 1 proportion z interval. After you find it in your calculator, it's prompting for x, where you're going to type in 323, and it's prompting the n, which is the number of people that you have, and it's asking for the confidence level. So you're going to type in 0.9. After you push calculate, it will actually give you an interval. Copy it over. It also gave you a p hat. The p hat I already written down, but it is 0.23. So you don't need to calculate the p hat separately. What you can do is you can just start typing in your x's and your n's into your calculator. It'll spit out an interval. Very important in our class is to give an interpretation of the interval that you found. So we found that approximately 21% to 25%, so I'll round this to, actually I won't round this, so I'll keep the numbers that they gave me. This is the percentile of people that have landlines. No, the students paid with their education by student loans. So this is my success. So, sentence. With 90% confidence, the proportion, or the true proportion, of students who paid for education with student loans should be between 21.158% and or 24.853%. So these are the percentile that you were given. This is why all of the numbers in one proportion z interval is going to give you a 0 first. Now, before I finish this example, there's one thing that we forgot to do. And what I need to do is I need to go back at the very beginning. I have a little bit of space over here. In order for you to do any of the problems in 7-3, you need to check two conditions. Take NPQ and NP hat and NQ hat and make sure that it's greater than 5. All you really need to do is just write this down. The hat is 23. This hat is 77. All you're really doing, I'm just going to move this over a little bit. This number I already know it's 323, which is greater than 5. This is how I was able to get that number in the first place. 1404 times 0.77 should be even bigger than that. So 1081, which is certainly greater than 5. Checking these conditions is a must. You need to do this every time you're doing any of the problems in 7-3. I do have one more example that I wanted to cover on the confidence intervals. This is example 7-10 in your book. A survey of 6,000 people found that 58% said that they would take a ride in a fully self-driving car. So the ride in a fully self-driving car, or take a ride in a fully self-driving car, that's your success. The 58% that is given to me and the 6,000, those are the two numbers that we need to use. A survey of 6,000, meaning that I asked 6,000 people, that's my N. If I'm given a percentile, if I'm already given a probability of success, that's my sample. My sample said that 58% said yes. So what they did is they didn't give me an X, they gave me a P hat. And they also want 90% confidence. The formula calls out for the P hat, but a calculator calls out for X. In order to find X, you take N and you multiply this by P hat. Because by definition, P hat is X over N. So in order for you to find X, well, you know that 58% off 6,000 said something. So that's what you do. You find what's 58% of 6,000. Those are my zeros. There's no sixes. Now, this number cannot possibly be a decimal because this is how many people said yes. You know that binomial distribution is a discrete distribution. This must be an integer. Otherwise, your calculator will freak out and give you an error message. So make sure that that x is an integer. And the rest is a calculator. You go into stats. There's no S. Go over to tests. Go down to one proportion z interval. It's asking for x. Type in 3480. It's asking for n, which is 6000. And it's asking for a 90% confidence level. You put 0.9. You calculate. And it spits out the interval for you. With a p-hat of 0.58, n is 6000. I already have all of this information written. I don't need to rewrite it again. But before we continue, two things. Let me just move this over. Number one, check np-hat and q-hat. 6000 times 0.58 is equal to that 3480. I already have that number. Just make sure that you have greater than 5 somewhere on your piece of paper, otherwise you'll have points taken off. And then you need the Q. The Q is the 42% that said, no, I would never drive in a self-driving car. You take the 6000, you multiply this by 0.42, you will get a slightly smaller number, but still large enough in order for us to be able to use normal distribution. So this is the idea. In order for the binomial stuff to make sense in a normal setting, the sample must be large enough. The large enough isn't all that huge. It just needs to be np-hat greater than 5 and nq-hat greater than 5. That's all we want. And then you give your conclusion statement. With 90% confidence, the proportion of people who, and then you copy the phrase of your quote-unquote success, who would take a ride in a fully self-driving car should be, with 90% confidence, the proportion of people who would take a ride in a self-driving car is between 56.952% and 59.048%. That's it. We don't need anything else. I will end the video here and continue on the next video with the rest of the examples.